I see.
We have a lot for planning also.
I see.
So can I do a first check of all the presenters? I can see Alessandro. Yes, good. Team, where is team? Ah, yes, sorry. Mihai, no, is the name? Where is Mihai? Okay,
Yeah.
Nicolita. Is that the good way to say? Mihai Nicolita. Okay.
Here.
Hans, where is Hans? Not yet. I believe he's not yet there. And after that, we'll have the coffee break and 3 more presentations. And Andre is saying that after discussion, no, we'll have the presentation of the field trip.
No. It will be tomorrow.
Ah, yes, tomorrow. Yes.
No. I
Yes.
meant that there will be one talk made from the field. From the
Yes, for tomorrow. And what will be the time for discussion?
The time for discussion, if we look at the program, so discussion is appointed at 6:30 Moscow.
Yes.
-1, and so much time as we need.
So 30 minutes, the maximum will be
maybe
there?
30 minutes, 1 hour, so
okay.
As much as we need. We are not limited.
Okay.
Not limited.
So 2 minutes to go.
Yeah. Ale, have you received my message by email? Yeah. Switch on your microphone. Ale, can you switch your microphone on? Okay. Have you received my message about tomorrow? Yeah. Okay.
I also answered it.
Thank you. Fine. So Tobias will convene the first part, and you will convene the second. Thank you.
Thank you very much.
It's nice to see colleagues from everywhere. So
yeah.
I think now with these new technologies, we have more facility to meet persons that are at quite distance. So, and I also say hello to Marcelo that received me, Marcelo Mota in Brazil, and give me a nice trip along nice rivers. So I think we are on the time. So I thank to Andre that asked me to convene this session. But first, I want to give my tribute to Rob Westaway, because I remember well the good moments that we passed in the field, and also during the very intense discussions during the meetings, and after that having beer or in other moments. So, and also because of very nice publication he made. So I move on to the first presentation of Alessandro Fontana. Yes, please, you can start.
Can you see my video?
Yes, perfect.
Okay. Just a moment. Okay. So it's a very pleasure to be here, even if we are not in the same place. But I want to show you today a presentation about a minor river in the northern Italy on behalf with my colleagues from the Department of Geoscience in Padova and also from the Ministry of Cultural Heritage in Italy, Matteo Frassine, because this is a common, let's say, researcher that have been sharing geological, stratigraphical, but also archaeological things. And the common point is that using the archaeological artifacts and especially the structures is possible to date sometimes for some time frames in a very detailed way, also the fluvial deposits that generally, I speaking about the late quaternary, are based for the chronology on OSL or radiocarbon chronology that are the main pillars of our studies, but sometimes they are not able to pick the real time window with a very high precision. And we speak about Musone River. So if we look in northeastern Italy, this is Venice, okay? Adriatic Sea, this is the boundary with Slovenia and Austria. Musone is a minor river, is a palealpine river with a somehow small basin, small catchment. And it flows in the proximal part of the alluvial plain that was formed by the other rivers, the main alpine rivers like Brenta and Piave, that in this part of the plain is very gravelly, while differently in the distal portion is fine dominated, the alluvial plain. It is important that Musone, on the contrary, is a fine dominated alluvial plain. So if we look at the positional systems, we have that this is the megafan of Brenta, this is the part of the megafan of Piave, of Montebelluna, that is dating to pre-LGM. Brenta started in LGM and now is still active. So Musone was flowing, and it's flowing in the interflow between these major systems. And it's something particular because it is not related to main glaciers, neither is related directly to the sea level. So it's something, let's say, disconnected by the major forcing that were playing an important role in the construction of the alluvial plain, like glaciers and sea level for the northeastern Italy. And what is the motivation that we started this study is because you can see this line, and this is the path of a new highway that they are building in the last 10 years. And is you can see that is perpendicular to the main alluvial systems. And these construction works gave the possibility to have a lot of stratigraphical windows for looking and investigating the stratigraphy, the shallow stratigraphy of the first 5-10 meters of stratigraphy. And then I will come back after in this image, but you can clearly notice that Musone, that is also receiving its main tributary, that is Lastego, is flowing along this yellowish part, that is the alluvial plain that it formed. And then on the left, you can see something that is more orange, that is the Brenta megafan, and something on the right is reddish, that is the Montebelluna megafan. So the cuts, the windows that we saw, the stratigraphic windows, are characterized in some parts out of the Musone alluvial plain by gravels, tens of meters of gravels, one stacked on the other body. But in Musone, that is large, let's say a couple of kilometers, the alluvial plain, the width is about a couple of kilometers, you can see a lot of fine material and some paleo channels. Here you can see an archaeological excavation that completely removed the infilling of one residual channel because it was filled by archaeological remains also. And the methods are, let's say, somehow classical, but I want to stress exactly this point that working together with the archaeological survey, we could see all the stratigraphical outcrops that were put at the light by the archaeologists and also by some very long trenches. And then some words about the archaeological settings. Is the ancient structures that have been recovered here are mainly dating to the recent phase of the Bronze Age. That is dating to this period. You see, that is just a couple of centuries. Then there is also a minor phase in early Iron Age with a time gap of, let's say, less than 200 years. And in the Middle Bronze Age, and then especially in the recent Bronze Age, the whole northern Italy was affected, was characterized by blooming of settlements. So there is a phase of an important, intense phase of population. So we opened here very large excavations, as you can see. And coming back to this one, as I spent a few words before, if you look at this orange, yellow, orange, so the two megafans and the interfloor, I can show you a DTM of this area with this perspective. So you can see Musone, that is, the source is here. Then here is receiving the Lastego, its major tributary, and then is flowing in the alluvial plain. You can notice here the colors that highlight the megafan of Venta and the megafan of Montebelluna. You can see that the bays in the catchment are quite little because they are something like 55 square kilometers. But I want to stress your attention about the fact that the main elevation, the maximum elevation of the Lastego reached 1,200 meters. And on the contrary, the maximum elevation on Musone reached less than 500 meters. So there is a very high energy, topographic energy along this major tributary. If we look on plan form, you can see on the map, this is the main site that we excavated. The highway is going more or less in this direction, okay? And I can show you a detail of the main spot where we had a lot of excavation and coring site and geotechnical tests and other kind of information. And for example, in this part here, we have the deepest sections that are sometimes long more than 100 meters and up to 5 meters of depth. And you can see here, for example, that you have a series of buried soils, one on top of the others. At the bottom, at about 5 meters, 4 meters, we have the gravels of Montebelluna megafans that are of a pre-LGM date. I can show you one detail here. Okay, so you have pre-LGM gravels, and on top there is a paleosoil that developed mainly just before pre-LGM and then in the LGM. And then we have some soils dating to the late glacial and some deposits to also the Holocene. Here I marked just the major ones, the major soils, but we have also some faint, some very weak developed soils in this part. Where the circle, the yellow circle is, we also found one heap of road here that we radiocarbon dated to, you see, late glacial. And this is one of the only places in northern Italy where it's possible to find this kind of late glacial deposits, because in the rest of the alluvial plain, during this phase, the fluvial system was deeply incised in the plain, in the proximal plain, but also in the very distal plain. So there are no much deposits of dating to late glacial. According to all the data that we have about the subsoil of this area, we could calculate the thickness, but also the volume of the sediment brought by Musone during the late the post-LGM. It's about something less than 60 millions of cubic meters, up to 7 meters of thickness. I can show you one section here, one stratigraphic section is a sketch. And you can see that Musone deposits are overlapping the Brenta megafan and the oldest Montebelluna megafan, up to 7 meters in this. Okay? We have several of these sections. I just show you this one. It is interesting because in this point that I already mentioned, if we look at the present geometry, the style, the fluvial style of the channel, is very affected by anthropogenic activity and is, let's say, characterized by low sinuosity, straight pattern. And then here you can see in an aerial image that is magnified here, that you can see something related to wandering and also not only single channel, but we can see in the Holocene sequence, okay? So, concentrating in the major archaeological sites, I can show you the map of the different paleochannels that we detected here together with the archaeologists. And I start with paleochannel A. So this is the archaeological excavation. This was part of the village with the boundary ditch that was surrounding the village. The paleochannel was going this way up to 3 meters of depth here. It's filled by sands with the gravels in the basal lag. I can show you the section that was dug here. The section, according to the archaeological artifacts that have been found inside, we know that this river was active for about 1 century. This section here is reported here, and you can see the different layers that are prograding inside the channel. And inside we have also some artifacts, so we know exactly the age of the progradation. If we look here in a deeper section, we have that the filling of the channel is characterized by cross-bedding sands, but at the bottom we have the gravels of the lag layer. And if I magnify here, you can see some large shards of pottery dating to the Bronze Age, to the first phase of the recent Bronze Age that have been eroded, okay, and transported during the activity of this channel. If we move to Paleochannel B, that is clearly very sinuous, this was already a residual channel during the Bronze Age occupation. During the recent Bronze Age is meandering, the depth is about 2.5 meters. And we have that inside was completely filled of artifacts interfingered with very fine, with fine sediments, so silt and clay, organic clay sometimes. So this was was no more active during the activity of a paleochannel, but was a residual one, but still open. And people was living here, but also in the external part. If we move to Paleochannel C, you can see that is has a larger width and is also a bit straight. We know that is an erosive channel, as the base is very erosive and was eroding the Bronze Age site, and it's filled by sands and gravels. So you can see a picture from here, from the infill, that you can have some cluster up to 3 centimeters. And so this is related to high energy flood, that occurred after recent Bronze Age, And it's related probably to a flood of high magnitude. If we move to I skipped Paleochannel D, I move to Paleochannel E. It's a bit more complex. So from north to south, you can see that these are the boundaries of the Paleochannel. That was a residual channel filled during recent Bronze Age, and after was filled by gravels in the early Iron Age. So here we have Iron Age structures, but below we have some Bronze Age structures that were living along the Paleochannel. And the age of the sands that is filling at the top, these paleochannels are related to the archaeological structure. So we know that the flood that occurred in the last phase of activation, that is more characterized also by some gravels, occurred after early Iron Age, because it's partly overlapping also on Iron Age structures. We can see one example from here of the sandy infill that is covering, you can see magnified here, some Bronze Age artifacts, and we have also ripples and the ripples in the infill. And at the top, in this part, I can show you another section where you have the gravels, the, let's say, gravelly sands of early Iron Age that are partly also carrying some Iron Age artifacts, but they are burying and also reworked and partly eroded with the bottom, the residual channel that was already filled with Bronze Age material. So if we try to summarize what I showed you about this, let's say, little system, if you consider compared to the other alpine, to the alpine system existing in northern Italy, we have that Musone is a unique window because you can see fine deposit dating to the post-LGM in the proximal gravel plain, where you normally don't have late glacial deposits and also early Holocene deposits. Musone is still at the top of the pre-LGM surface of Montebelluna megafan that in the rest of the plain has been completely plowed because it's cropping out. So you can't see the pristine, let's say, natural soil profile of this unit, only here. And the study area is at the boundary probably between the area where also the debris flows coming from the mountain catchment could reach the alluvial plain. Apparently, also not only for the data that I show you about this site, but also for other sites along the highway, meandering channels started in the area not before the Bronze Age. So, and I skip to the last point, it is possible that also some anthropogenic influence occurred, maybe in the slope of the channel and the sedimentary discharge due to the human activity, because also the mountain catchment was severely affected by clearance of woods due to the use of wood for fuel and other purposes. And we know that during the first part of the Iron Age, we have some high magnitude floods. So we have also the witness of this kind of situation. So I thank you for your attention, and I'm here if you have any question. Thank you.
Thank you, Alessandro. We have 1 minute for discussion. Who wants to ask? Meanwhile, I will say that is a very detailed study case. I would like to have more samples collect for OSL dating, even if not now for the next year. So you could collect and store them for detailed studies later on, because it's quite nice to have detailed geometry, also artifacts, so archaeological structures, industries, and to have numerical dating will be very outstanding. So anyone? I cannot see people asking. No? If not, we move to the presentation by Tim Winkels. Tim just informed me that he has a problem with sound. I don't know if you already solved it.
No, yeah, my apologies. I have a sick child at the moment.
Yes.
So I'm multitasking a little bit. So I'm going to try and play a recording I made for IAS, which is basically the same presentation. So I think it should work. If it doesn't work, just put it in the chat and I'll do it live, and then it's fingers crossed that everything works out. So just let me know if it doesn't work, okay?
Okay, perfect.
And I'll be there for the questions afterwards. That will be okay.
Okay, go.
Hi, my name is Tim Winkels. I'm a PhD candidate at Utrecht University. And my talk today is going to be about the sedimentary architecture of typical short-lived meander belts in the Rhineland Delta. So most studies looking into the spatial patterns in sedimentary architecture of meander belts do that for locations like this, where we have a well and nicely preserved rich soil morphology, which makes it relatively straightforward to determine the positional context within the meandering system, but also the evolution of the system itself. And by correlating that with various subsurface data sets, we end up with these sedimentological models. However, most of these studies are done within a valley setting, which is of course in sharp contrast to the deltaic setting of the Rhine-Meuse delta. For example, when we look at fluvial activity within a valley, that's often constrained within for longer periods of time, promoting self-reworking of the system itself. Well, if we look at the delta setting, the much wider
team, your screen is not shared.
It's not working?
No.
Screen is not shared.
Oh, my apology.
Can only hear you, not watch
Then we're
you.
gonna.
Can you repeat?
Yeah.
It's
Okay. Now you see my screen?
Now,
yeah.
now we see.
Yes, perfect. Perfect.
Okay. My apologies.
Okay, please begin.
Okay.
Hi, my name is Tim Winkels. I'm a PhD candidate at Utrecht University. And my talk today is going to be about the sedimentary architecture of typical short-lived meander belts in the Rhine-Meuse delta. So most studies looking into the spatial patterns in sedimentary architecture of meander belts do that for locations like this, where we have a well and nicely preserved rich fill morphology, which makes it relatively straightforward to determine the positional context within the meandering system, but also the evolution of the system itself. And by correlating that with various subsurface data sets, we end up with these sedimentological models. However, most of these studies are done within a valley setting, which is of course in sharp contrast to the deltaic setting of the Rhine-Meuse delta. For example, when we look at fluvial activity within a valley, that's often constrained within for longer periods of time, promoting self-reworking of the system itself. Well, if we look at the delta setting, the much wider unconstrained delta plane facilitates the periodic repositioning of fluvial activity through avulsion. So here we see all the mapped channel belts of the Rhine-Meuse delta. So here's the delta apex, and here's the present-day coastline. And we see a lot of different systems. However, the majority of these systems is only active for roughly 1,000 years. And you can imagine that in combination with the continuous aggradation in the delta, this leaves behind a quite heterolytic subsurface, which again acts as a substrate for younger channel belt systems. And also because we have this aggradation instead of nicely preserved rich fill morphology, we end up with these ridges, which further complicates the studying of these systems. So one of the questions that we had is, to what extent does meander belt evolution at different stages therein govern the sedimentary architecture of these deltaic meander belts? So when we're talking about different stages in meander belt evolution, we're talking about distinguishing between the main activity and the abandonment stage deposits. So the main activity stage deposits are the deposits which were deposited during the migration of individual meanders, so when the system was active, while the abandoning deposits are split between the sandy shallowing narrowing deposits, which are deposited during the abandonment process, so when the channel is losing discharge, and only after it's fully lost its discharge and no permanent flow is going through the channel anymore, we get this muddy fine clastic infilling, which we call the residual channel deposits. So we want to attempt these reconstructions for a local case study. So we selected the Stuyvenberg channel belt, which has a typical period of activity of roughly 800 years. So it's a typical short-lived channel belt. And we selected a 5-kilometer stretch of this channel belt, where morphology was still a little bit preserved, but mainly because we had a lot of digitized boreholes in this region, so over 4,000. The majority of those only reached the top of the channel belt, but we also have some deeper ones, which give a bit more insight into the sedimentary architecture of the system itself. So how did we approach this? The residual channel was easily mapped from the LiDAR images. So we mapped a continuous depression. But for the abandoned channel, we had to use a bit more empirical approach. So we used the relationship between channel depth and transferred bed slope angle to determine the width of the abandoned channel. So the depth of the channel we got from various boreholes and cross sections, while the transverse bed slope we got from literature, from comparable systems in the Rhine-Meuse delta. And if we combine that, we come to a first order approximation of the width of the abandoned channel, which is roughly 100 meters for the Stuyvenberg. We also wanted to reconstruct the rich soil morphology as much as possible. So again, we could get some snapshots from the LiDAR imagery. So we had some localized soil depressions, but we mainly used the ample amount of boreholes in which we drew these cross sections, in which we could easily identify the higher ridges. So that's what we see here. So we reconstructed 3 different stages of meander activity, an early, middle, and end stage. And what we now see is that throughout the study area, we have different modes of meander migration. So here we see a downstream translation of the meander, while here we have a sort of translation-rotation combination, while this section is more or less characterized by a gradual expansion of the meander. So now we have a really nice framework in which we can put our sedimentological data. And I'm not going to discuss everything because I don't have the time to do that. So I'm just going to focus on 2 cross sections, cross section A and cross section B for now, because I think that already really nicely illustrates the point I want to make. So this is cross section A. So here we see the Stuyvenberg sand body. In orange, we see the main activity sands. Here we see the abandonment sands and the residual channel. And if we then zoom in a bit on the main activity sands and we look at the median grain sizes, which are over here, we see a division between the upper and the lower bar deposits. So lower bar deposits, which are over here, you see there's some variability in median grain sizes, but there's no clear vertical trend. While the upper bar deposits show a clear fining upward trend. So there's a clear subdivision between these upper and lower bar deposits. We've then compared that to these abandonment channel sands. Overall, they are slightly finer. But also the fining upward trend already begins all the way down here. So there's no clear distinction between the upper and the lower section extent of these abandonment channel sands. If we then go to cross section B, the whole thing is a bit more complex. So stick with me. So again, we see a clear distinction between the upper and lower bar deposits. So lower bar deposits still have are characterized by no vertical trend in median grain sizes. However, there's a clear distinction between this, the northern and the southern section, with a lot of limited variability in median grain sizes in the southern section. So almost all the same values, while the northern section is characterized by a lot of variability, but still no vertical trends. The upper bar deposits are a bit more complex. We see both fining upward sequences, so clear fining upward, same as in cross section A, but we also see coursing upward sequences. So sediments becoming coarser when we go higher up in the channel belt. So this is more complex. But again, if we compare it to the abandonment channel sands, we see that these are slightly finer. And also here, the entire sandy sequence is characterized by a fining upward sequence. So overall, if we compare cross-section B with cross-section A, we see that cross-section A has a far more uniform buildup than cross-section B. So now we want to see if by adding positional context, we can maybe explain why these differences occur. So if we now look at cross-section A, it covers an extent of the channel belt, which was formed due to the gradual expansion of this meander. Which basically means that also the position along the individual meander band doesn't really change along this cross-section. Well, cross-section B is already a bit more complex because this section was formed due to the downstream translation of this meander. So instead of a uniform position along each individual meander, this has changed throughout the extent of this cross-section. So in our paper, we go into much more detail of how this affects the sedimentological buildup of this channel belt. But overall, the take-home message for now is that it really depends on how this meander developed over time. And it really impacts the sedimentological character of these channel belt deposits. If we then look a bit further, we also see that even within these main activity sands, we see clear convex scroll bar patterns, but also concave scroll bar patterns. If we then take some deep boreholes from those locations, so here we have within these convex zones, we see these relatively coarse sandy deposits, corresponding to that what we saw in this lithological cross sections as well. But if we then go to these concave zones, we see something completely different. So we see far more fine clastic material, and even if we have sandy deposits, it's significantly finer. So again, this points out that it depends on where you are within your meander belt and how it formed. These are the so-called counterpoint bar deposits. So some conclusions: the overall sedimentary architecture depends on meander evolution and the positional context therein. So first, there's a clear distinction between these main activity sands and the abandonment stage sands. So we see that there's a sedimentological difference. They're a little bit finer, show some different trends as well. But also within these main activity sands, it depends on how the meander was formed in relation to how it is built up now. So, and also finally, we can argue that the short duration of these channel belt systems greatly reduce the internal complexity. So if, for example, for the Stuyvenberg case, if we would have continued fluvial activity, this would result in chute cutoffs or even more internal reworking of its system, even further complicating the overall sedimentary structure. So if you want to know more, I would urge you to read our paper. We just submitted it, so hopefully it will be accepted soon. But for now, this is it. Thank you for your attention.
Thank you, Tim.
Hey, thank you very much.
So you managed to solve the problem with sound?
Yeah, my daughter thought it was so boring she fell asleep. So I hope you guys were a bit more interested.
Okay, time is open to discussion. Who wants to put any? So I'll start with a comment.
Yeah.
I also found the architecture with this type of rivers quite complex because they change in space so in a fast way. So it's difficult to make correlations if we don't have a lot of stratigraphic controls. It's almost impossible. In your opinion, how can you use this type of record to get some information about climate event? I'm talking about to the result of them in terms of discharge. So this, because I think this could be nice to know because of your expertise.
Yeah, that's a really interesting question. One of the big questions is when does this morphological change happen? So what kind of discharges do we need for this river to meander? So I think that's always been a tricky one to answer. The nice thing is, I think these type of systems, for example, hold some records, possibly some records. I have some idea about it. So for example, if you look at these concave accretion zones and you look at systems that are active now and where they are formed, you see that there's like these small lakes involved in there as well. So these potentially have the chance to have these like high resolutions local flood records, which we could use to reconstruct the discharge history of this type of channel, and then potentially link that to the type of discharge also needed for morphological change. Because I think that's one of the key issues here, I would say.
Okay, Jess also wrote in the chat, because I think there is no permission to activate sound.
No, there must be permission. There must be permission.
So I'm asking to activate sound. Yes, but I can read at least to save time. He says, Jess says, thanks, Tim. What is your overall aim in knowing what the meander belt lithology is like? Groundwater resources, gravel mining, or is more blue skies?
In this case, it's dike safety or river. So my project focuses on looking at the the safety of human-made embankments along rivers, which for their strength are largely dependent on the subsurface which is beneath them. So this project aims in better understanding the processes behind that local variability beneath these dikes.
Okay, thanks. Jess is saying that he could not connect sound because he's in a quite loud airport. Okay, any more question?
Can I ask?
If not, can we? Yes, please.
I'm registered as co-organizer. That's why I have no option to raise virtual hand. Sorry.
I was not saying your. Okay,
no,
please,
I
Andre.
just my physical hand. Tim, can I ask you why do you know the time scale of the development of your channel systems? How have you dated them?
Well, that's a nice thing. What we have in the Rime News Delta, because we have like one of the first maps I showed with all these different channels. They're all really nicely dated with like residual channel dates, in this case with C14, and also underneath levees and so. So we have a nice chronological framework which is already in place, which allows us, so we have already a head start before we start this type of research.
Wow.
Okay, we still have time, but I can see that Mihai wants to jump to his presentation. So, okay, next presentation by him, please start.
Thank you so much.
Hippolyta.
Yes, I just tried to see if everything works fine. So do you see my presentation, I assume?
Yes, okay, it's perfect.
Okay. Thank you. So I would like first to thank you all and the organizers that allow me to present my work, which is a work in progress. But let's say it has some preliminary conclusions that can be presented and are important. So landslide and river interactions, we know that generally river incision trigger landslides. And I will show you a study case when also the triggered landslides not in a classical way also influenced the river and its evolution during the Quaternary period. So first, I will show you the general setting of the study area. So we are in a plateau area outside the Carpathian Mountains. We have elevations which range between 80 to almost 400 meters. We are basically in a Miocene platform from a sedimentological and geological point of view. So the layers are almost horizontal. They have very low dip toward the southeast, toward the Black Sea. And at the upper part of the landscape here, at around 300, 400 meters, we have basically a layer of sandstones. And below we have mainly mudstones and sands from a geological point of view. This is visible also in a crossword profile. We see here the maximum altitude in a 10-kilometer swath, the mean and the minimum altitude, and also the cross-section in the study area. We speak here about Bahluietz River, which is a tributary of Bahlui. Bahlui is a tributary of Prut, which is flowing into the Danube River, and Danube is flowing into Black Sea. So we have here the Quaternary, the Pleistocene, and the Holocene control of the Black Sea. In the study area, we have managed to obtain some dating information about the landslide, which was inferred to be later Pleistocene in age and proven before MIS3. We know the upper bound of the landslide because we dated the terrace deposits of the river. Because the river valley was clogged with landslide deposits, basically the river started to deposit floodplain deposit over the landslide. And in a further let's say, step after the incision. Now we have basically a terrace. This terrace, which has heights between heights above the present day channel between 7 to 20 meters, basically was dated to be before and after LGM, which is an age which is similar with a dated terrace of 20 to 20 meters elevation above the present day channel at the mouth of the Bahluetz River. Here we are very close to the upper part of the catchment. Basically, the river has around 10 kilometers in length at this position. Here you see a detailed representation of the present-day floodplain, upstream and downstream, the channel bed, the channel bank, and the presence of the terrace. This is a drone picture of the study area. The most important point is here. There is an archaeological site from the Neolithic period, late Neolithic, early Bronze Age. And you can see it's a rural area. We can also see the rough topography of the landslide. This is the reconstruction of the geology, which was checked in the field based on the literature, and also the geometry of the landslide, which is basically obtained from natural exposures, but also with the help of geophysical surveying. We used DRT and shallow seismics. The area was also geomorphologically mapped on high-resolution LiDAR DEM in order to be able to observe the geomorphology. The results were obtained in, let's say, trying to show that this site is very important from a geoheritage point of view, but later I have seen that it's also very important from a geomorphological and from a fluvial point of view, beside the landslide. The study area, which is quite important, is presented here with the shaded DEM. Basically, this Mander island cutoff was incised after the Neolithical period, and starting with the 20s also was eroded. So we have here 12 meters high exposure of the landslide and fluvial sediments. We also managed to date the setting with radiocarbon from organics in the floodplain deposit, OSL, and also, let's say, the modern fluvial floodplain deposits also with radiocarbon. So in the upper part of the landslide, we obtained very old ages, up to 44 to 46,000 BP, to 20,000 in the median part. Probably the upper part is something like 15,000 BP. This was indeed showed in the bottom part of the landslide deposit and the covering the floodplains deposit, having two dates, 21,000 and around 16,000 BP. So we also used OSL to also try to see what is happening here, because I told you about the incision. But the OSL date sometimes can be tricky. You see that probably there is a lot of residual luminescence in the deposits, but we were able to say, based also on archaeological artifacts, that this situation here, geomorphological situation, is due to a later incision in the old floodplain deposits. This OSL date is a little bit older, but actually, let's say it would fit with this model. Downstream the study area, we were able to date the floodplain deposits at 4-meter depth to around 4,000 BP. So I told you that upstream and downstream we have a modern, let's say, a new Holocene floodplain, while in the area with the landslide deposits, actually we have a very old floodplain which became a terrace. Unfortunately, the floodplain sedimentology is mainly qualitative because we didn't start yet the, let's say, the sedimentological description. We want to do that, and we are open to suggestions. But basically, we have a floodplain type that can be associated with confined, fine texture sediments with high energy. We believe that this is due to the rough topography of the landslide body. In some parts, we have deposits consistent with lateral accretion, while in some parts, we might have some flood basins. You will see some pictures. The lamination is present, but also we have a columnar structure with many fissures that we believe it's post-depositional. So this is a deposit of lateral accretion from the area where we obtained the radiocarbon dates, which go up to 46,000 BP. You can clearly see the lamination, but which is very different as a orientation, as a inclination. But we have mainly fine sediments, clay and silt, very compacted. We have also the geological Miocene shells, spherical pebbles, and also sandstone slates. And we also find from time to time sand pockets in this deposit. We believe that the confined nature of the floodplain, which was and of the river, which was flowing over the landslide deposit, created this lateral accretion, which is quite strange at some points. For example, here we have in the same site from top to bottom, from vertical to horizontal, and with the lack of stratification. But then we have also a situation like this, where we also might ask if maybe we have some sliding, but we were not able to, the present point, to prove this. So we consider it also to be an accretion. So this is the main site from which we left with this idea. We have the landslide deposits. So these sandstone layers, they were in the same layer. And due to the landsliding, basically they faulted, and then they flowed to the floodplain area. We have clay stones in between these sandstone layers. Here we have the terrace deposit. Here we believe that is basically a flood basin. Why? Because probably if you see this landslide topography, rough landslide topography, probably during high flows, the water was coming in these flood basins. What is really interesting is that these flood basin deposits actually are the highest in the present day topography. So it might be logical that they were filled only during high flows. Of course, the incision destroyed, let's say, a part of the initial landslide topography. We still work on the geophysical part to explain the situation. On top of the floodplain terrace deposits, we have buried soil and the archaeological deposit, which is late Neolithic to early Copper Age, sorry, not Bronze Age, Copper Age. The same flood basins, sometimes with slates of sandstones on top. The idea is that the landslide, they continued after this initial big failure. So we have a lot of landslide, mainly rockfalls inside and on top of the floodplain deposit. You can clearly see here. And there also there is a paleo relief inside these floodplain deposits. So the main conclusions and further work, because it's clear that we need to further investigate sedimentologically the floodplain deposit. Basically, we were able to prove the upper age of the landslide, of the initial landslide, which covered the channel or the floodplain. Also, the upper Pleistocene age of the fluvial cover. We can say the landslide is pre-MIS3. The fluvial cover, which became a terrace now, is covering the upper part of the Pleistocene and the initial part of the Holocene. There is an overlay. And the present incision, or the incision of the present channel, is basically mainly Holocene in age, as was shown in the downstream part. Also, there is work needed to define geometrically the landslide. We used shallow seismics, but it's considering the depth, it's clear that we need to perform a borehole to see if there are deposits older than the landslide. So in this way, we will be able to constrain very well the landslide. And also, basically, we need to do a lot of sedimentology. Thank you very much.
Thank you. So, time for questions. No? I would like to know, what is your opinion? What is the interpretation that you can give to only have the record of the terrace on the intermediate area of the long profile? Because I saw on the figure that you was only present at the middle part. Yes.
Yes, it's present only where the landslide deposits are on the floodplain. Basically, upstream and downstream, we have a very wide floodplain with middle to early Holocene deposits. Only in this area along the river, we have this Pleistocene terrace present.
And why?
Yes, because of the landslide. So the landslides covered the floodplain. So the river had to flow over the landslide deposits. And later in the Holocene, during the incision, only this area remained with the Pleistocene deposits. Upstream and downstream, we had the normal incision during the Holocene, and then the aggradation of from the lower Holocene period. So
Okay.
this is why we said landslide and river interactions, because the landslide was crucial here to create the terrace, the floodplain deposits, and the terrace.
Okay, Jeff also wants to put a question, please.
Yes, thank you for your interesting contribution. I just wanted to ask, you are talking about one landslide. Does it mean that there was only one landslide just in the longitudinal direction in the direction of the river?
No, I speak about one landslide because I work mainly on landslides and I consider as a compound landslide, but actually the material was flowing from both the hill slopes, and it's clear that there are multiple events, but we are not able to present day to say how many. So we consider compound landslide, which also has a relict landslide. So the relic landslide actually is in discussion here. We cannot say how many were events.
Your argument is the direction of the sedimentary structures, or what are your arguments?
Yes. So we recognize the lithology of this Miocene sediments in the area, and these layers of sandstones are basically geological. and they have continuity. They are basically tilted.
Okay, thank you.
You're welcome.
The next question. No. Andre, can we move to the next one?
I had a question, Pedro. Can you hear me?
Ah, okay. Please.
Sorry, I haven't turned my video back on.
Ah.
Oh no, I've got a misbehaving false background. I just wanted to ask about geoheritage, because you mentioned geoheritage, and I agree this is important, a nice example of something that's really quite exciting. So are there mechanisms in Romania to provide geoheritage preservation for this type of thing? Incidentally, there's a larger scale comparator in I think the Yangtze River, is there, where there's a huge landslide or founded mass that's incorporated into the Yangtze sequence. So that's just one I can think of off the top of my head. So there are interesting comparisons, but this would be an interesting geosite. And do such things exist in Romania, and can you get this added to the coverage?
Yes, so basically we started working on dating landslides with the help of archaeological layers in 2016. We published already in GeoHeritage Journal several sites where landslides are considered geoheritage sites. And at that point, we hypothesized that actually this should be a Pleistocene landslide. So now we were able to prove it. And we already submitted another paper for the GeoHeritage Journal. At the local level, we are trying to argue that this site should be included as a county important site, and later to be able to include it in the in a national inventory. But all sits in the results regarding the age, because proving a Pleistocene age to the site. Yes, so we are working toward this. This started from GeoHeritage, and
that's excellent. That's excellent news. Thank you very much.
Okay, we have to move to the next presentation by Hans.
There is a question in the chat. Sorry. From JC Zondervan.
But just put the question that was already replied. It was about the arguments for the interpretation of the movement to landslides.
Okay. Sorry.
So that's why. So can we move to the? Yes, thank you, Hans.
Yeah. Okay. Can you see my screen well?
Yes, perfect.
Okay. Very good. Yeah. Yeah, okay, good afternoon, everybody. I'm Hans van Rodolz from Leipzig University, and I'm very happy to present you our study about the fluvial architecture of buried floodplain sediments of the Weiße Elster River in Germany that was revealed by a combination of core drillings with different kinds of geophysical measurements. So all we know that fluvial sediment archives are very valuable to know about former flooding phases and about paleoenvironmental changes in the catchment, as well as about naturally or human causes. However, a precondition for the proper interpretation of fluvial sediment archives is to understand their fluvial architecture that is shown here on this picture taken from a publication from Bart McCuskey, and the fluvial architecture that is the three-dimensional arrangement and genetic interconnectedness of different kinds of sediments. As everyone can imagine, this task is quite easy to do in river systems that were recently incised. Here a photo showing outcrops at the Algedi River in Georgia, where you had different outcrops, and by looking at these different outcrops, it was quite easy to study the fluvial architecture. However, if we go to floodplains that did not see young incision processes and therefore the sediments are mostly buried today, this task turns out to be quite challenging, as you can see here at the example from the Mulde River in central Germany. So to address this issue in buried floodplains, the most used way is to drill transects through the floodplains. Yeah? And as you can see here at the example of the Wetter River in Hessen, a work that was done by Peter Huben and colleagues some years ago. And you use the information from numerous individual drillings to build up 2-day figures of the buried alluvial fluvial architecture. However, a main problem remains, and that is that generally there's no information about the continuation of fluvial structures in the surroundings, such as, for instance, channel patterns, unless you have the possibility, like Alessandro Fontana and his colleagues, to excavate those structures, what is of course very excellent. However, that is often not the case, so that the continuation of such structures is often not known. So therefore, the goal of the study was to take, just here as an example, the map of Peter Huben from the Wetter River. It was to get information about such buried structures in larger areas by transfer the information from the 2D transects to their larger surrounding areas. And we did this by applying several methods. On the one hand, we built up the conventional 2D transects by first measuring the electrical resistivity tomography, the ERT, and subsequently we drilled vibropore drillings that were leveled by DGPS measurements. But furthermore, we also measured the transect surroundings in 3D by applying the method of electromagnetic induction, EMI. And I think some of you don't know that method, therefore some words about this. EMI uses such a tube that the person carries that walks over the interesting surface. And on the one side of the tube, there is a sender that emits an electromagnetic field. And in the underground, this electromagnetic field evokes another electromagnetic field. And both fields are finally received at the other side of this tube by a receiver. And finally, you can get information about buried structures from different depths. And furthermore, you have a DGPS receiver to get accurate positioning during all measurement time. So we worked now in a joint geoarchaeological project in the Weiße Elster floodplain here in central Germany. And the Weiße Elster River has a catchment of a bit more than 5,000 square kilometers and a mean discharge per second at the confluence with the Saale River of about 25 to 26 cubic meters. We are working in the northern part of the catchment area because here we find a well-developed floodplain with a width of up to 2 kilometers. And we work here in 3 different study areas. And in the following, I want to concentrate on the northernmost study area, that is here the transect number 1 in Salsitz. Here a view at the topographic situation. You have here the floodplain with a width of about 1 kilometer. You have the river, and you see here from the LiDAR DEM the different terrace levels relative to the main riverbed. And furthermore, you see here our transect that had a length of about 950 meters. And in yellow, you can see here the area that was measured with electromagnetic induction that averaged about 75 hectares. Looking at the results, first at the 2D results from the transect. You can see here the results of the electrical resistivity tomography. And in blue colors, you see here areas where we have fine-grained sediments at the surface, that means flood loam, whereas here the areas in the east, southeast, with with the red coloring and yellow coloring, where we had higher electrical resistivities, and that means that we have coarse-grained material, that means gravel, near to the surface. And this information was very valuable for us because this allowed to space the drilling according to the expected sediment types. That means in case of the flood loams, we spaced them in distances of 10 meters, and in the southeastern part, where we have the gravels, we spaced them in distances of 20 meters, what finally saved time and money. Yeah, here a view at our 81 drillings of the transect. You can see here with the blue line in the lower part, that's the limit between gravels at the base and finer grained sediments above. And you can also see that those finer grained sediments that show up to 3 intercalated paleosols. And we subsequently attributed the elements of the fluvial architecture that were proposed by Peter Hoben 2007 for rivers of the temperate zone. That means at the base, these gravels were attributed as braid plane or channel deposits. Above, we often find in yellow, shown here in yellow, sandy bed forms. And finally, we have in red, shown here in red, the over floodplain finds. That means that's a flood loam. And this flood loam shows up to 3 intercalated paleosols. And furthermore, we have here different channel structures that are either filled with anorganic material or with organic material. Yeah, looking at the chronology of this transect, you can see here that with the triangles, that these are brick fragments, and we know that in our region, bricks were only introduced during the Middle Ages. That means these youngest sediments cannot be older than the Middle Ages. And furthermore, we did radiocarbon dating things and are currently doing luminescence dating. So, however, the latter are still in progress, but the radiocarbon datings tell us already something about the rough chronostratigraphy. And that means that below this oldest paleosoil, the lowest third paleosoil, there must be found the oldest floodplain sediments. And we know from the radiocarbon age of this organic channel filling that these braid plane deposits and the incised and filled channels, they must originate from the late Pleistocene to early Holocene. The next generation of sediments were the fine-grained flood loams, that according to our radiocarbon datings must have been deposited during the Neolithic period, here between 7,500 and 6,000 years. And subsequently, you see here the second generation of fine-grained sediments that were deposited between about 4,000 and 2,500 years with several age overestimations due to the reworking of older charcoal material. However, we could attribute it to the Bronze to Iron Age. And we also see by the intercalating paleosol here in the middle that there were at least 2 different main phases of flood loam aggradation. And finally, we knew already by the brick fragments that the youngest sediments cannot be older than some 100 years. Finally, we also got to radiocarbon dates of about 300 years maximum. That means that these sediments must be very young. And we know from historic maps that here in the southeastern part, the river did not largely shift its course. And that means these sediments were deposited between 300 and 200 years. That means during the final Little Ice Age. Now we're having a look at the transect surroundings. Here's a signal of the electromagnetic induction. And you see already that here in the south and the center, you have here some areas with very low values. That means blue and yellow, blue and green colors. And low values are attributed to coarse-grained material, sandy to gravelly material. Whereas here in the central and northwestern part, we have areas where we generally have higher values, and these are attributed to fine-grained material. That means to flood loams. And furthermore, we also see here some linear structures with higher values, and we interpreted those as paleochannels that were subsequently filled with fine-grained flood loam material. However, these are just geophysical data, and geophysics is not just influenced by grain size, but also by other effects, such as, for instance, water content. Therefore, it was necessary to couple this geophysical information with hard data from the drillings of the transects. First, a view at the paleochannels. You see here the drillings, and here I mark with the 4 letters A to D. I mark paleochannels that appeared both by the drillings in the transects and in the EMI measurements, as I will show you here. You see here these paleochannel structures marked with the letters, and these letters or these positions show up here again, yeah, and you see that exactly at these positions we see such linear structures with high values of electromagnetic induction. Sorry, yeah. So, and that means that obviously most of those structures that we had interpreted as paleochannels are obviously real paleochannels. Yeah, furthermore, a look at different sediment generations. Here again, yeah, the drillings, and I showed you that here are in the center and in the northwest, they are quite thick, fine-grained flat loams, whereas in the southeastern part, these are much less thick. And from the datings, we know that below this lowest Paleosoil, these are Neolithic flat loams of the first generation, and directly overlying the basal gravels, whereas in the northwestern part, above the basal gravels are directly flat loams of the second generation from the Bronze and Iron Age. And finally, where we don't have mighty flat loams, we know that these fine-grained sediments originate from the Little Ice Age. And with this information, we can now go back to the image of the electromagnetic induction. And so we see that the oldest sediments, the oldest fine-grained sediments, that means the Neolithic flat loams, they are obviously only preserved island-like here in the central floodplain at, if we take just the measured area, at about 16% of the surface. We know that this area in the northwest is dominated by the sediments from the second generation, that means the Bronze to Iron Age, and this averages around 40% of the surface. And here in the south and in the central part, these are obviously areas where the youngest sediments from the end of the Little Ice Age are dominating at about 37%. And that also means that obviously after flat loam sedimentations and before or during the deposition of new flat loams, there was obviously the large lateral erosion and removal of older flat loam. That means the oldest generation was obviously largely removed before the second generation here was deposited. And the same holds also for the second generation. That means also during the last phase of strong fluvial activity, there was obviously large-scale lateral erosion. Yeah, just at the end, a short look at the larger scale pattern. Here from the LiDAR DEM, you can recognize some visible floodplain structures here in the lowest terrace level. You see here paleochannels, and here you see obviously scroll bar structures. And we know from our detailed investigations that these obviously here belong to the lowest terrace level. That means they belong obviously to the last period, the late AGM period. This strongly meandering channel pattern. What we don't see in the DEM, but we know from our combined approach, is that also during the Bronze and Iron Age, fluvial sedimentation was obviously linked with a strongly meandering channel pattern, whereas prior to the deposition of the oldest Neolithic flat loams, there were obviously low sinuous channels in the basal braid plane that originates from the latest Pleistocene to early Holocene. That means, ideally, our combined approach is complemented by topographic DEM analysis to obtain as much information as possible about the former fluvial architecture. And at the end, I am now coming to the perspectives. I think, or we think, that our applied method combination allows for a much better reconstruction of the fluvial architecture and dynamics of buried floodplains compared with just transects alone. And we think that this is a very promising approach also for future fluvial geomorphological and paleoenvironmental studies in currently buried floodplains. Thank you very much.
Thank you. It's amazing the detail that you showed to us. And we have already here on chat a comment from Jess saying, how long did you take to produce the MII you showed? And what is the average view over a certain depth? How long does, how deep goes the it?
Yeah, okay, I start with the first part. So this work was actually done by a bachelor student, yeah, the EMI measurements. So they are under supervision of also our colleagues from the geophysics departments of the UFZ in Leipzig, the Environmental Research Center. And the field work took around 2 weeks. It was a lot of walking, and the post-processing then was during his bachelor thesis, I would say it was about 3 months. Yeah, that was the first question. The second question, yes, there is no depth dimension because we just have 3 depths. And this is not enough to do the inversion to get real depth. And that means, as you are right, this is just averaging, yeah, over that depth. That means the uppermost 6.7 meters. And I can, I can show you here just for your interest. These are the other 2 depths. Yeah, these were 2.2 meters, 4.2 meters, and 6.7 meters. And finally, we decided for the deepest conduction, because we got most of the information out of it. But unfortunately, inversion is not possible, yeah, because of this low data density. You would need 6 or 7 depths for this.
Okay, we have another question by Andrea Kirchner. You want to?
No, actually, I think Hans just said that the depth is somehow a problem, because I mean, I'm not a geophysicist, but I actually wanted to know, your stratigraphy is really fine, and you separate like 3 different floodplain levels and so on. But for the EMI values, you just get a single value, right?
Absolutely, yeah, absolutely. You're right, yeah. That means you just get the rough structure. Yeah, I mean, as I showed here, I go back. Yeah, you just see here. Yeah, you just, or I go to the original. That's better visible. You just get here. You see in this area here, you have very low values. That means the gravel are obviously quite close to the surface. Here you see in these other areas, okay, the flat loam is obviously thicker, and then you see these linear structures. That's all you get. Yeah. However, the complementary information about the different generations, yeah, about the ages, about the paleosalts, yeah, you need, of course, the drillings, and finally you need the datings. You need a real stratigraphy. Yeah. That's why just the geophysical measurements without the hard drilling core data, yeah, that's not enough. Of course, not enough. However, you can spatially scale up this 2D information to the larger areas, and then you understand, yeah, those structures, for instance, that you can see in the DM. You then know, okay, these young channels, yeah, that I showed you here in the DM, okay, and these scroll bar structures, this belongs obviously here to the youngest generation, yeah, of the final little ice age. Yeah. So it has to complement each other.
Okay, thank you, Hans.
I just want to comment on your section. You put at the geological section. Can you show it? You placed at southeast only on floodplain deposits only the phase 3.
Excuse me, I did not understand it.
Could you show the section, the geological section,
yes,
with interpretation?
Yes,
yes, that one. So my comment is on at southeast, you put only the phase 3,
yes,
over the gravels, but probably that's because you could not identify the levels of paleosols.
Yes.
And maybe you need the drilling because it's quite surprising not to have the 3 phases here.
No, I mean, this is information derived from the drillings. And I have to confess, these paleosalts in these floodplain deposits, it's a large problem to identify them. Yeah, because before I worked in Georgia in the Caucasus region, and you saw the paleosalts, it was very clear they were dark, they were clay, and so on. However, here in Central Europe, we have the large problem, you hardly see them. Yeah? So it's really hard to recognize by very small changes by their sedimentological properties. And therefore, we normally, I go just back to these detailed drillings, yeah, we drill maybe 4 to 5 drillings individually, and then we put them next to each other, and then we see, is there an anomaly that is holding through all those cores, or it's only found in one core? And in that case, in the latter case, we say, okay, we remove it, it's just a singularity. But if we find the same kind of structure in several cores, we say, fine, that is it's a real paleosol. And we also did so in the eastern part, and we had no hint, yeah, that that there are paleosalts. So, and therefore, just from the field work, yeah, that was quite hard stuff. I can be very sure to tell you here are no paleosalts. So I don't want to say there was a shorter term surface, maybe 10 years, but we don't see it. Yeah.
Yes. Yeah. Okay, we have to move for the coffee time. We have now 10 minutes for a little relax, and we move again in just after. Okay.
Probably it's done.
Yes, but yes. Okay. I hope they are online. So next presentation will be by Gregory Fabian. Where it is?
Mr. Fabian is cannot log in, so maybe I'll present it once more. Paweł Przepióra here. Hello.
Yes.
Yes, Fabian cannot log in. He's
Okay.
offline now.
Okay, and you have the presentation. Okay.
Yes. So
okay, you can start.
Okay, so I will share the screen. One moment. I hope you see it. Yes. Everything is fine. You hear me? You see the presentation?
Yes. Okay.
Okay. So this time the presentation that's supposed to be Gregory show. It's about the geological structure of the Świślina River Valley near Doły Biskupie. Maybe you remember this site from the last presentation I showed. Our presentations are very connected together. This time will be more geological structure of the valley floor here. And on the picture, you can see how our students and scientific team working in the hard scientific life we have. So, Świślina catchment is located in the central Poland, in the central part of the on the Świętokrzyskie voivodeship. And this is a pretty big catchment area, but we are concentrate our work on the lower part of the catchment, where is a study area located with the Doły Biskupie town. And short information about this river. This river have 35 kilometers length, and it's a typical meandering river. But also there is important fact that there was built in the central part of the river a reservoir called Wióry, built in 2005 last years. There is a very young reservoir. Also, the geological structure, the older parts are located on the also Mesozoic margin of the Cross Mountains, mostly on the Triassic sandstones in the part of the entire part of the catchment. But most important is that entire catchment area is covered by the loess. Loess covered almost every part of the catchment area, even with the area in nearby our site. So you can see that only the older rocks are visible in the places where we have the loess cut by the gouges and the small valleys in here. And this time I will present here 3 different profiles. 2 of them you remember perhaps. The one is located on the terrace and the floodplain. The one of it is the historical profile. And the last one, and the most important for now, is the profile as W1 on the lowest upland. How it looks like it's very interesting structure visible on this profile, especially that we have some bird soul complex here that we dated for the late Pleistocene time, and bird gouge that more visible is when we show it by the orange dashed line here. We try to date it also by the OSL method, and we gain the material below this gouge about 60,000 years, and the material filling this gouge is about 1.2 thousand years. Also important is that we found here very interesting layer insert of probably the flat sediment insert, built mostly by the sharp edge coarse material. Beneath of this material, we found many shells of the Malacofauna. So you can see it on the picture on the right side. Also, the more precise picture show us how these structures looks like. So this structure is very high from the modern riverbed level. So we know how this the scale of this structure on this profile looks like. We have two visible layers of the buried soils, buried gouge, and of course that flat sediment inserts. And we know that that loess in here is supposed to be redeposited from the upper parts of the catchment. Also, the buried gouge here is very interesting because we can see probably the part of the mouth of the top of this still visible, probably Pleistocene valley, shown in the green dashed line in here. The topographic position index gives us a chance to see this morphological changes in this part. And we can say that probably we have here rejuvenated later maybe and cut it again by the different Pleistocene valley in this fact. So we have the gouge filled with the sediments and no longer exist. Only this green dashed line give us some information that there was some kind of valley in this place. And perhaps the mouth of it was located in the place where we have the profile here. Again, we can see how hard was take the samples from this profile. We again the specialist with the lines and working on the lines in here with the students and the friend. And we take the samples, we make the grain size analysis of this material, and we see that most of the material is typical loess material, but with some inserts of the sands in here. Most of those sands are located especially in the modern soil level and of course in the buried soil complex. And this modern this buried soil complex also have the low counted organic matter and the carbonate in this place. The terrace, in fact, maybe you still remember the last presentation, we have the profile, historical profile made in this place, and we still know that there is many traces of the anthropogenic impact, especially the metallurgical impact, many charcoals, slags, and iron ore deposition. And of course, we mostly have here typical silty and fine sand material accumulated on the terrace of the Świecina Valley in this section. In fact, the floodplain area is built very similar. Also, we have mostly the material, fine material, some sands, but it's supposed to be redeposited because we have still here some artifacts I showed before. Also, very interesting is fact that we have very small, but still very well visible in the lithology layer of some kind of flood, giving us information that during this flood, the younger material become less carbonate and pH become lower. Also, in this material, the heavy metals contamination become higher, so we can connect this with the metallurgical activity that we have found in this only in these sediments in the upper part of the profile. Many small microscopic iron balls that probably supposed to be redeposited from the upper part of the Świecina catchment area. From where those artifacts came from? You remember that this area became a part of the Old Polish Industrial District, and as you can see now on this picture, the almost entire catchment area is on the prehistoric and Roman period metallurgical activity area, where the archaeologists found from the last many years many bloomeries sites in here. So here it is. This is again the picture we showed before, showing us how intense is this range of the meteorological activity from the prehistorical times in here. Entire upper part of the catchment is become the red and orange, showing us the interpretation of the Blomeyer slag sites inventory for almost 100 sites for 1 square kilometer. It's very lots of them. We have here also location of the known exmitted Blomeyer sites. And the study area is located where we have less than 30 slag sites in 1 square kilometer, but still it's very high level. Our interpretation is that perhaps those slags, microscopic and microscopic slags, are redeposited from the upper part of the catchment, but it has to be done before the reservoir in the central part of the catchment was built, perhaps. So maybe the rest of the material is supposed to be in situ. Who knows? This needs more analysis in this area in the future. Only one place where we have the modern metallurgical activity in this area, just like before we showed, it was remains of the 19th century sheet metal factory in the Nietuliska, but this site is located downstream from the Śliśnina in the estuary to the Kamienna River, a few kilometers from our site we presented. So there is we cannot connect this with this slags we found the upstream in the Śliśnina, in the fact. We made the cross section from this site, and we made this kind of summary for this. We can see that geological structure here, we got the younger sediments cover the Triassic sandstone and mudstones. We have at least 2 levels of the terraces and the lowest upland. We know the lowest upland supposed to be, we can see, creating some kind of flat terrain, maybe before it was some kind of terrace. But all the lowest in this profile supposed to be redeposited from the upper parts. That's why we have here the carbonated, and we found many there is a many sandy material in it. The terraces, in fact, supposed to be younger. Probably they are younger, but there is no explanation how those slags inside those profiles that was made in 1958 they were there. The Klatka says that the bigger slags supposed to be in situ, and they can be connected with nearby Blomeyer sites, or maybe the medieval metallurgy activity in this fact. But the smaller parts, in our opinion, supposed to be redeposited from the upper parts. We don't know in the fact, but in the fact we know that in the floodplain area, those macroscopic slags supposed to be redeposited because they are accumulated in the upper part of the profile under the flat layer, showing us that there was some kind of change of the fluvial system in here. And also there is no historical data about the medieval activity of the metallurgical activity in this area. So only we have left is the archaeological sites of the prehistorical metallurgy activity in this place. So the younger part of this section of this floodplain can be somehow show that not exactly all the artifacts give us the same information. Perhaps they are prehistorical time, but redeposited, that seems that material redeposited here is supposed to be younger. And of course, it have to be probably redeposited before the reservoir, the bigger reservoir in Viury was built in 2005. Small conclusions about this site. We have the lowest upland built of 2 series separated by the buried soil complex. There are 2 late Pleistocene buried soils soils from the 33,000 years and 50,000 years. And the buried gouge in the lowest upland was filled with the younger loess. Of course, the precise dating was problematic here, but this giving us information that this gouge supposed to be functioning about 60,000 years ago, and later filled by material, younger material, lowest material from the upland, and filled at least very young time from the early medieval time, 1.2 thousand years ago. The very coarse sediments, in the fact, they can indicate the occurrence of the catastrophic flows in the last millennia. Also, this dating gives us probably connected with the medieval times, but this insert is very hard to date it, because we think that it can be also probably younger. We don't know, but this kind of coarse material with the malacofauna can be also transported during the flash floods after the breaking the dam in Viury that was made in 2001. When this reservoir was built, the dam was break and there was a big flash flood. So we still have open mind for this kind of events can operate during not only the medieval and human activity from the last centuries, but even from the last years. And of course, the macro and microscopic traces of the iron spherules in the sediments of the terrace and the floodplain, connected with the metallurgical activity in the Świślina Valley with the bloomeries, probably with the bloomeries, because the entire catchment area is the big archaeological site of the prehistorical metallurgy activity, and there is no historical data about the younger, that means modern and medieval prehistorical metallurgy activity in this area. So in the fact, we think this can be connected with the bloomeries, but more analysis are needed to show this theory. And thank you for attention. Again, this is one of our students, how hard scientific life they got in our university working with us. Thank you very much for attention.
Thank you. We have time for one question. No? So it's time to move to Andrei Panin. You can start.
Okay, thank you very much.
Okay, can you see my presentation?
Yes, perfect.
Okay, good. Well, I will talk on the sources of the River Volga, which is the largest river in Europe, but we will talk on its very source when it's a rather small one. Volga is a very well-known Russian river, a kind of a symbol of a country, but we will see that it is, in fact, it is understudied, and it has more mysteries than clearance about the history of its development. And we wanted to show it, to illustrate it during our failed field trip last year, but well, I hope we will still show it in our presentations and publications. This is the Upper Volga. It's 1,000-kilometer stretch, which was intended to be visited during the last year field trip. And now we will talk about the very, very upstream part of Upper Volga, which contains the upper 150 kilometers of its course. And also an important here is the so-called Upper Volga area, you can see it here, which is abundant in lakes left by the last glaciation. Here you can see the last glacial boundary at the LGM. The rest of the territory was subject to the Zaalian or Muscovian isotope stage 6 glaciation. And there was already half century ago, there was a discussion on the development of the Upper Volga. The first concept was that it was formed immediately after the MIS-6 deglaciation, and the upper terrace of Volga has the MIS-6, MIS-5, MIS-4, H, something like that. The other concept, more popular, I would say now, the other concept was that at the LGM 20,000 years ago, there was no Volga Valley. There was a system of large proglacial lakes. You can see here the dashed contours, and only after the last deglaciation, the Volga Valley has started to develop. So to address this discussion, we started two key sites in the upstream. First is Bolshaya Kosha, which is named, it's a village named after a small tributary of Volga. You can see it here. The other is small town of Rzhev. There are 70 kilometers between each other by the river. And you can see also that Bolshaya Kosha is in the very vicinity of the last glacial boundary. I have to say that the position of the LGM boundary here is still under discussion. Here is one of the versions of this boundary. Well, at Bolshaya Kosha, the very upstream site, we have drilled a long profile. Here I will show only a part of it without this gentle slope. Here we can find, to see it in more detail, let me show two parts of it. The right part of it contains the uppermost terrace, which gave us OSL ages around 90,000. The upper date is from the cover deposit 90.5. Here is also cover deposits. Then a high step to the lower terrace, and other terraces gave the late glacial ages. Here is, and also here is a floodplain with a number of radiocarbon dates that show that by the middle of the Holocene, 5,000 to 6,000 years ago, the incision stopped. So the terrace staircase was formed from LGM to the mid Holocene. And you also see that the highest terrace is of the LGM H, and there is no more ancient alluvium in the valley. Importantly also is that this terrace is on the great sand body, which was dated to the very ancient times. Before it's probably MIS-7 or even MIS-8, and this is typical for the Volga Valley, the occurrence of such large sand body, but of very ancient time before the Zaalian glaciations. But there is no alluvia older than the LGM that belongs to the modern river Volga. And the left part of the profile is another terrace 2, which is in fact only a couple of meters below the highest terrace, but it gave rather older dates because of poor bleaching. All these are OSL luminescence dates. The other terrace staircase was studied at Rzhev, key site, 70 kilometers downstream. Here the valley is much more narrow, and we also have the highest terrace, which is the widest one here, also the highest step to the lower terraces, and the staircase of the late glacial OSL dates. Unfortunately, we could not date the highest terrace here because of the very coarse gravels that compose it. But the similarity of morphology of the terrace staircase let us correlate this highest terrace, and it is also 15 to 16 meters as in the cautious. So very, very similar, almost the same terrace staircases at different parts of the valley. To estimate the age of terraces, we used the statistic Bayesian approach. We used the Beacon software to create not age depth models as is usually done for geological sections, but here we reversed this and created elevation age model in two variants. First is where the elevation of each individual sample was plotted, and here all samples from each terrace were plotted at the elevation of the terrace surface. And this variant B looks better for me, and it allowed us to estimate the age of main terraces, and you see that the highest terrace is around 21,000. It's around local AGM theory. And also important is that the next terrace is very similar in age, which means that the incision rates at the very beginning were very high, which makes an important point for us. Well, then we hypothesize on the causes of river incision, and there are classical possible reasons why the river may incise. First is lowering of the base level, and we have excluded this because this is a very upstream part of the river system, very far from base level. Second, changing of river slope. If slope increases, for example, due to the tectonic tilt, the river may start to incise, and given the proximity to the glacial boundary, we must take into account the glacial isostatic adjustment effects, and this is a point for examination. And second is increase of river discharge, which may be caused by climate change, again due to the proximity of the ice sheet by the water flux from the melting glacier. And second is also classical cause driving river development is a change of drainage basin. Well, let's look through all the possible, all the rest reasons of the incision. First, glacial isostatic adjustment effects. We used the ICE5G model by Peltier, not ICE6G, because in ICE6 the glacial boundary for our region is not correct, so we cannot use it just for our region. This is the model realization for the LGM for the whole North Eurasia. It's interesting because it shows the occurrence of the glacial forebulge at 100-200 kilometers from the ice sheet boundary, and we can find also its effects in the upper Volga, but not in our part. Here is a more close look to our regions. Here are our two key sites, and this is the deformation of topography deformation at LGM relative to the present day, and we can see that the surface, due to the glacial loading, the strip adjacent to the ice boundary was tilted in opposite direction to the river flows. So it must have affect the river slope. And when we also studied several time slicers, and but LGM and present day are most important for us. You can see from here, these are our two key sites, and you can see from here that at the LGM glacial uploading, tilting due to glacial uploading caused almost twofold decrease of slope, and after deglaciation, the slope increased twice. So it may have affected the river behavior, but we do not find the difference in the height of the terraces, which must have been seen if this was the main reason of the incision. And second, we don't see any difference in the size of channel alluvia, which also, so if the slopes at the LGM were too gentle, then the alluvia at the LGM must have been much smaller in size than the present day, but we don't see also this effect. So probably this factor worked, but as a secondary one, not the main reason, the main driving factor of the incision of the river. Well, second is, well, increasing discharge. First, we know climatic effects. We know the effect of large increase of river runoff in the late glacial. Here is the last reconstruction of the Volga, of the river runoff over the Volga basin for the LGM. You can see that the discharges increased almost twice, both for all Volga and for upper Volga in particular. This climatic epoch was dated through from the large meanders, large meandering paleo channels, which were used to reconstruct the discharges. And we can see that this epoch occurred from 18 to 13,000 years ago, so after the LGM, but this factor cannot explain us the large incision that occurred before 19,000. So particularly at the LGM or immediately after it. So probably the climatic effect also worked, but also as a secondary factor. Well, and the last chance to establish the reason why Volga was being incised is to check whether its catchment area could have changed. And well, this is the Upper Volga lake area behind the last glacial boundary, and it is connected with the rest of the Volga basin with so-called Selizharovo breakthrough valley. Selizharovo, it's a small town here. This breakthrough valley and enters the rest of the basin immediately at the Bolshaya Kosha river confluence. Here is how it looks like. This is a rather narrow valley, incising into the terminal moraine, which is thought by some researchers as the MIS2, but we know that now that it is MIS6 terminal moraine. Here is like it looks on the topographic map, and this is the drilling profile, which we made in the very upstream part of this valley. Here is like it looks in the landscape. It looks rather gentle, but the elevation range here is almost 30 meters. You can see the car, it's 20 meters below you. And well, here is the profile with luminescence dates. The blue is the late glacial lacustine deposits, which was dated to infinite dates, which tell us that these are probably the MIS6 glacial lacustine deposits. Then the white bottom of the valley covered with not very coarse alluvia of the late glacial age. You can see the luminescence ages 13, 14, 15,000. And after that, the floodplain with mid-Holocene radiocarbon ages. So we reconstructed the history of the valley the following way. So after the MIS6, there was no valley. During the LGM, there was a breakthrough with formation of this hollow this hollow, and then during the late without sediments because it was an erosion form. During the late glacial, the river Volga River migrated over the white bottom, and after that, in the mid-Holocene, there was an incision phase, which is interesting because the Bolshaya Kosha mid-Holocene was the stop of erosion, and here there was an impulse of incision here. Well, if we look now at the map, we can see that if we hypothesize that, and now I think we have proved it, that this valley was formed only in the LGM. So before the LGM, this lake area did not belong to the rest of the Volga basin. So this was the catchment boundary at that time. After that, at the LGM, this part and after LGM, this part of the basin have joined, and we can see that if we take the present day basin at Rzhev, we can see that this inclusion of this upper part increased the basin area twice. Before the LGM, the source of Volga was the Bolshaya Kosha river, and after the LGM, after the joining of this upper part, the source of Volga is now where it is now here. So probably this process was the main driving factor of the incision process from the LGM. And here is the conclusion. The upper terrace of Volga has the LGM-H, not MIS-6, not MIS-5, but if we go directly to the conclusion 5, the absence of the older alluvium does not mean that the valley also has the LGM-H. We suppose that the old alluvium was just destroyed due to the increase of the power of the river after the inclusion of the upper part of the basin. So river incision started at the LGM and stopped in the mid-Holocene, and it was caused mainly by the increase of discharge due to the catchment changes. Due to the inclusion of the uppermost part of the catchment because of the breakthrough of glacial meltwaters through the former watershed. And after the LGM, some contribution to the incision was made also by glacial isostatic adjustment effects and climatically caused increase of river runoff in the late glacial, but the main reason was the change of the catchment area. Well, thank you much. I'm over.
Thank you. Questions? Yes, Alessandro, please.
Thank you, Andrei, for bringing us around, even if in remote modality. My question is about, probably for a reason of shortening in time, you didn't go in detail about the facies of the deposits that are on the upper terraces compared to the lower one. So I'm wondering, do you have any clues about this?
Yeah, sure. We have about 30 cores there and several sections, and all the isotope stage 2 terraces from LGM to the beginning of the Holocene are composed of gravels with sand matrix. Some gravels are rather coarse, so we had difficulties in sampling them for our cell. And some terraces also are covered by sands, but these sands are mostly of Aeolian due to the Aeolian redeposition of former alluvia. And typical overbank phases, overbank finds started to accumulate only in the Holocene. That's just briefly about. There are also more interesting points about it, but
David also wants to put a question. David.
Yes, hello. Thank you, Andre. That was very interesting. And I know that our late colleague would have been very interested in that as well. Before I congratulate you and agree with you that the change in the catchment and the breakthrough valley is behind most of the incision you report, I would want to know whether neighboring valleys, in particular valleys with the same relationship to the glaciation, show none of the incision that you see in the Volga. Because if they did, then I would start to question whether a special event like this can be the explanation. And the type of incision and even the timing that you describe is very similar to Northern Britain. And this is the bits of the Westaway paper that I had to skip through because I was going over time. But I did mention his arguments with Dick Peltier, and I noted that you referred to Peltier's work. Essentially, if you're not on ancient Precambrian crust here, then an element of glacial-isostasy could be causing permanent effects of this scale. And this isn't reversible like the mantle isostasy that Peltier models. And this was the argument Westaway always put. And he made more of an argument of it than he needed to, and he didn't really have fallen out with people like he did, because in fact the mantle effect is everywhere, and it is more important. It's bigger. This crustal effect, if Westaway is right, is really quite minor, but where you are on younger crust, it is an important effect. And to me, it potentially explains why we get these post LGM terraces in Northern Britain where there was glaciation. That sort of material of that age, evidence of that age, is underneath the river in Southern Britain when you're a long way away from the glaciation. And this puzzled me enormously. And as with so many things, Westaway had the answer. Whether he's right or not remains to be seen. But I offer that as something to discuss.
We have another question by Jeff, please. Jeff? Jeff? No? Jeff?
Jeff's muted.
Yes.
Oh, sorry.
Okay, perfect.
You hear me? Okay.
Yes.
Andre, I think one should be very careful with attributing a river incision solely due to the increase of runoff or water increase in water discharge, because all depends on the ratio between the increase of water discharge and sediment discharge. Sediment load of the river is almost always accompanying the increase in water discharge. And if the sediment load increase is more important than the water discharge, you will have aggradation instead of incision. So did you have any idea about the sediment load that was accompanying this event of increase in water discharge?
Thank you. Thank you, Dave. Thank you, Jeff, for valuable comments. Well, just a few words to Dave's comment. Thank you for pointing at Westaway's ideas. We have accumulated some evidence that these GIA models do not work, at least properly, if not to say they do not work at all. But well, I don't say it, but at least in our region, they seem not working much properly. So maybe this underestimation of the mental effects by Westaway, maybe that is one of the reasons we should think it over. Well, Jeff, about the ratio of sediment load and discharge. Yes, it's a common effect over the most part of the Russian plain and also in Europe. The LGM and the most part of the isotope stage 2 is the epoch of river aggradation and formation of accumulative terraces with increased depth of alluvia. here in the Upper Volga, we don't see this aggregation effect at the LGM because the thickness of alluvia of the LGM and lower terraces is almost the same. So we don't see this LGM aggregation, which is typical for other valleys more distant from the last glacial boundary. And also to Dave, we don't know the history of the adjacent valleys. I mean, along the boundary of the last glaciation here. We started Volga different side. And I can say that downstream, this incision effect in the Volga Valley, it decreases. So 500 kilometers downstream, there is no so much incision. And there are some evidence of climatical aggradation at LGM rather than some, well, other origin of aggradation. So we tried to examine all possible reasons for the incision. I listed them in my presentation, and we have arguments pro and contra in all cases. And if you had more time, or if you had a real coffee break to talk to each other, I would show it, but probably in the paper on this presentation. I will write it.
Okay, we have a last presentation, but just after we have the discussion, so we could use that time. Okay. So the last presentation is by Pavel. Yes, you can start, please.
Can you hear me?
Yes, but not the presentation yet.
Okay, I will share the screen. Forgive me that I am without video. I have some problems with connection, internet connection.
Okay, can you click on PowerPoint? Yes.
Okay,
good.
So here we go. Good afternoon, ladies and gentlemen. My name is Paweł Rutkiewicz, and I am representing University of Silesia in Katowice. And I would like to show you my presentation about charcoal production for the needs of historical metallurgy from the area of Silesian lowlands from the Małapanew River basin. And at the beginning, I have to say a few words of introduction. In this study, the subject of charcoal burning related to the iron smelting industry using water wheel was under investigation. The first information on the use of water wheel comes from France from 12th century, and as well as from Hungary and Sweden. Historical sources indicate that for the study area, those type of activity began in the 14th century and continued to the 19th century. And the period from the 17th to 20th century was prosperity period. We know also from the historical sources that at least 52 large iron centers prospered here. I have to say also that until the 19th century, the primary fuel in metallurgy was charcoal, and large amounts of charcoal for the needs of water wheel powered metallurgical centers were obtained through a controlled process of dry distillation of wood in charcoal hearths. And you can see this, the example of charcoal hearths in this archival picture on the left side in this slide. And a charcoal hearth is understood as compact, most often round piles of wood, often made of straight and relatively thin poles, branches, and sometimes split trunks. And the construction was covered with turf, with the air supply controlled to the holes in the hearth. And the process of dry distillation took place inside them. And the process could last from few days to even dozen days. And the landform left after single heart we called charcoal head remains. And now I will move to the aims of the study. The first aim was identification and inventory of the landforms left after historical metallurgy here. The second aim was analysis of the internal structure of those landforms left after historical metallurgy. Then the next aim was dating of those landforms and the sediments inside them. And the last aim was to determine the scope and scale of the environmental changes which resulting from the historical metallurgical activity. In this study, we used a wide range of methods. And first of all, we've made a historical and literature and cartographic materials analysis, which we determining the location of former metallurgical centers, and also we have collected some historical dates, especially about the functioning of the historical centers. After that, we used GIS methods, especially we used the LiDAR aimable laser scanning, and we used ASC files. Based on we have created shaded relief models, and after that the landforms could be identified. So the next stage of the research were field studies, and during which we can make analysis of relief terrain and measurements of selected charcoal hand remains. We can also make sediment pits and revealing the internal structure of those chosen landforms. And another methods, we have collected charcoal fragments from the exposures, and we can conduct it for the C14 radiocarbon dating in Krakow and Gliwice laboratory. And then the dates were calibrated using OXScale software with the 95% probability. And we have also collected more than 1,400 pieces of charcoals for the anthropological analysis to recognize the species of wood used for the charcoal burning. And okay, a few words about the study area. The study was conducted for the chosen part of Małopane River Basin. And we know that former metallurgical centers were located along river courses and utilized forest for charcoal burning located in the immediate vicinity. Therefore, detailed analysis of charcoal head distributions were performed in 4-kilometer wide buffer zone along both banks of the river channel from source to outlet. And we also choose the 9 former metallurgical centers for the detailed studies. And the Małopane is a meandering sand-bedded river with catchment area of 2,132 square kilometers and annual discharge of almost 9 cubic meters per second. The riverbed is cut in a dozen or so meter thick fluvial glacial sands of the Riss glaciation. There are 4 terraces in the valley, a Pleistocene terrace from 4 to 7 meters, 2 Holocene terraces from 3 to 4 and 1.5 to 3 meters, and a modern floodplain. And the terraces of Małopane river are covered with the agriculture of pine woods, while on the floodplain there are patches of ash alder riparian forests and poplar willow riparian forests, and also alder swamp. it will be important in the further part of my presentation. Okay, let's move on to the results. In the first step, shaded relief models were developed using ArcGIS software. And here you can observe the part of river valley with terraces also. And in the magnification, you can see a lot of charcoal hedge remains, landforms here. And based on these digital images, the identification of charcoal hedge remains was done. And we have here a lot of charcoal hedge remains, and those landforms were identified manually by naked eye. So it was hard work, and the detection of charcoal hedge remains was based on the following criteria: regular oval shape with diameter from 10 to 20 meters, slight elevation above the surrounding area, and it was noticed after the profile terrain, and also the presence of oval-shaped small hollows on the circuit of the form, and identified charcoal hedge remains were marked on the maps as a shapefile format which is a geospatial vector data, as you know, and the single charcoal hedge remain was marked as a point. So here you can observe how it looks like for the small fragment of the research area around the former metallurgical center. We have here a large number of charcoal hedge remains marked as red points. And also in this area around those former metallurgical centers, we have made the terrain field research. And finally, based on shaded relief models, we have identified more than 1,066 of charcoal hedge remains in the area of 902 square kilometers. So it gives us 184 landforms per 1 square kilometer. So it's a huge number. And you can notice that landforms recording the occurrence of charcoal hedge remains were mainly found in forested areas. They were covered from agriculture or forest activity, and they are present along whole course of the river on the both banks of the river. After the digital measurements and also the terrain measurements, we know that average diameter of charcoal hedge remain based on 60 random examples measured range from 12 to 20 meters, and the centers of all the remains of landforms are composed of elevated mounds up to 50 centimeters in height. These central mounds are surrounded by shallow pits with depths ranging from 10 to 20 centimeters, and the diameters ranging from 2 to 3 meters. So you can see even in this photo that those forms are very small and hard to identify in terrain. So the digital data is very important in case of analyzing and identifying this type of forms. And okay, so based on the number of landforms and information from written sources, we are able to estimate the volume of wood consumed for charcoal production over the centuries. So if we assume that a single charcoal herd volume equals half rotational ellipsoid volume, and we can assume that average diameter of single herd was 16 meters, and the height of single herd was 2 meters. We can estimate that volume of the single charcoal herd with 16-meter diameter was approximately 268 cubic meters. So if we multiply it through the number of the identifying forms, we can estimate that over the centuries, more than 44.5 million cubic meters of wood could be burned for the charcoal production. And now I will be talking about detailed study. For the detailed study, we have chosen 9 detailed locations along the course of the Małopane River, where we have made sediment profiles in 5 different charcoal herd remains for each location. And here you can observe the single charcoal herd remain with internal structure in this form. And here we can see the 4 basic layers. The first layer is forest litter, and the second layer is sand mixed with coal, ash, and small charcoal fragments. And third layer is composed of big charcoal fragments. And at the bottom of the profile, we have loose sand, and we have collected charcoal fragments from from those layers composed of big charcoal fragments. And those fragments, as you can see in these 2 photos, we have conducted it to the C14 dating and for the anthropological analysis. And here we have the first detailed location in the upper part of the basin, and here we have collected 163 charcoal fragments, and mostly we have identified Scots pine wood, but also we have small addition of alder and birch wood. So we know that those species were used for the charcoal burning, and all of the chosen forms, landforms, were dated on the period from 17th to 20th century. And the second location, the upper part of the basin, and here we have a wide range of species used for charcoal burning. The dominant species is once again Scots pine, but we have also the wood of alder, birch, oak, Norway spruce or larch, silver fir, also European ash. And once again, all of the forms originates from the 17th to 20th century period. In the next location, we have analyzed 171 charcoal fragments, and all of those fragments were recognized as Scots pine wood, and also all of the forms originates once again from the period from 17th to 20th century. The next detailed location, here we have analyzed 156 charcoal fragments, and once again the dominant recognized species was Scots pine. We have small addition of birch, Norway spruce or larch, and silver fir wood. But in this case, we have quite old landform, originates from the 12th to 13th century period, which is quite interesting because as I said in the introduction, the written sources dated the begins of the metallurgical activity here to the 14th century. So it's interesting. We have also a second landform dated on 15th to the 20th century. So it's quite a wide range. And the second landform was dated on 15th to 17th century, and 2 landforms dated on 17th to 20th century period. And the next detailed location, and here we have analyzed more than 100 charcoal fragments once again, and the same situation, and it was at the beginning. We have all recognized charcoal fragments was Scots pine wood, and all of the we have all of the forms originates from the 17th to 20th century. We have even one charcoal was dated as a modern sample. And next detailed location and the same situation once again, nothing new. And this is location in the middle part of the basin, and second location in the middle part of the basin, and once again the same situation. All of the recognized charcoal fragments are composed of Scots pine wood, and the landforms are quite young. We have almost we have four landforms dated as a modern samples, so it's quite complicated for me. And we have two last detailed locations from the downstream, and the same situation here. All of the charcoal fragments were recognized as Scots pine wood, and landforms were dated on the 17th to 20th century period. And the last location, and here we have little different situation, because we have despite the Scots pine wood, we have also recognized the birch, Norway spruce or larch, and silver wood in small addition, and landforms were dated once again on the 17th to 20th century period. And to the conclusions, first of all, we know that in selected area of Marapanna River Basin, there are more than 166,000 charcoal herd remains, and it gives us 184 landforms per 1 kilometer, which is quite huge number. And they are oval in shape with a slight elevation in the center, and this elevation is surrounded by shallow depressions, probably used for the water and tar removal. And the diameter of those forms runs from 12 to 20 meters, and probably about 268 cubic meters could be burned in a single charcoal hearth. And the second conclusion is that in the internal structure of charcoal head remains, we have characteristic layer composed of sand and charcoal, small charcoal fragments, and additionally we have big amounts of big charcoal fragments inside the small depressions around the central mount. And we know that mostly the coniferous species were burned inside the herds, and especially Scots pine wood, and the other species were used to a much lesser extent. And the next conclusion, according to C14 dating, we know that charcoal head remains mostly originates from periods of the 17th to 19th centuries, and we know that also from the historical sources that it was the prosperity period of metallurgical production in the studied area. But in few cases, it is interesting that it has been shown that the activity could start even a few centuries earlier than the historical sources suggest. And the last conclusion is that we can make some estimation, and taking into consideration the dimensions and of the landforms and the identified number, we can estimate that over the centuries, more than 44.5 million cubic meters could be burned for the needs of charcoal production in the identified charcoal hearths. And in this proves a very large scale of historical metallurgical activity especially on the forest communities, and charcoal burning could cause clear changes in forest areas or even the disappearance of those forest cover. And the comparison to the of the identified species with the contemporary vegetation does not indicate a transformation of the species composition of forest communities. Thank you very much for your attention.
Thank you. So time is open for questions. To start, I will say that could be very interesting to put some graph with the plotting of all the ages that you have, so we could see some concentration in some time interval, because we only have seen by sites. Okay. Do you have that plotting or not? You can provide a more specific intense activity for that.
Can you repeat your question?
I was saying that could be interesting to provide a plot of all the ages that you have in the same graph.
Yeah. I think about that. So I think that in the further research, I will do that, because it will be much clearer, I think, and it will be better to show the maybe chronology of the production of charcoal for those area. I think so. Yes, I will do that.
Okay. So Hans wants to make the next question. Please, Hans. Yes, Hans.
Thank you very much for this interesting talk. And I was really impressed by the enormous amount of charcoal kilns in your catchment. It seems that almost the complete area was somehow affected, and that means a very large human impact on the landscape and the ecological properties. And I'm wondering if maybe this large or the large amount of charcoal that is of course also remaining under such a former kiln will also change the soil properties. My question is, do you see any systematic differences of the vegetation between kiln areas and non-kiln areas? You said the tree vegetation did not change, but maybe in the lower vegetation something like this is visible.
Oh, yeah, this is very interesting question, and we didn't see the varieties between the area, between the plants on the charcoal head sites and on the adjacent area. So it have no sense in of this type of research in case of our study area. But I know that some kind of this type of research have been done in Germany, so not in our study area, but I know what you are talking about, because it has place, but in other study areas, but we didn't see that phenomena in our river basin.
Okay, thank you very much.
Thank you.
Time for another question or comment. So I take the opportunity to ask Andre. You show an older unit. For that unit, the ages that I could remember was older than 140,000.
270.
Okay, 170. So did you date it with the post-IR, or what was the dating method?
No, this single date was only by quartz.
So
just from this particular section, but we have maybe a dozen of dates from other reaches of Volga, all made by PIRR, and they are also not finite. More than 300, more than 400, so it's a very old.
So that goes for the next question. That is,
you might have heard the presentation by my PhD student Anna Utkina at LED 2021. She presented the old post-IR dates from the lower reaches of Volga at the luminescence conference.
So in your opinion, why we have this jump or this lack in record, in sedimentary record between this older unit, at least this one that you show, and the younger ones? Why we don't have a gradation, only downcutting or dynamic equilibrium?
I think it's just the consequence of the glacial history of the area. The stage 6 glaciation was very powerful. It deleted all previous geomorphology and left only geological bodies. So these geological bodies, after MIS6, they worked as a substratum for the new geomorphic processes. So that's I think the explanation of this chronological jump in sedimentary record. So we have this pre-glacial alluvial, probably alluvial, large alluvial bodies. Then we have teal MIS6, and after stage 6 we have a bit full sedimentary record.
So enlarging the discussion, I will say that in this type of areas, quite cold, we have these no record because of erosion by glaciers. In tropical areas, we have the opposite. So we have a lot of weathering. So normally we could only have as sedimentary terraces quite young, normally Holocene, but in some cases we have some strats. So that's I think we will find the most complete staircases in temperate climates. But I want to give this discussion to other colleagues, because we have time for this.
Yeah, we can now switch to the general discussion, I think, yes. Thank you.
It is already open, yes.
Yeah, can I start?
Yes, Andre.
Yes, I had a couple of comments to Marcel Blittner, but I don't see him in the list of participants. Maybe Hans von Suchodolec, who is a co-author of this presentation, may co-comment. And as I know, Hans also worked in its Georgian project and maybe led it, I know, from several publications on Alazani River and so on. Well, my first comment is about the age model. There was a very beautiful age model which took into account the sedimentation breaks related to soil formation. And my question was, how was the duration of the soil formation, how was it estimated? Because it was included into the age model. It's very interesting, but how did you know how long this or that soil formed without sedimentation? That's a question. And the other question is about the interpretation of the ages on the leaf walks. Marcel said that leaf walks pre-aged sediments that contained it and explained it by the erosion around 4 to 5 Ka. So by redeposition of old matter by the erosion 5 to 4 Ka. And I'm wondering in this case why charcoal gave so nice age model in stratigraphic sequence without any reversals. What we know, well, for example, the last presentation showed us that there are tons of charcoal over each river catchment that may be redeposited at any time. And so we also know that charcoal frequently gives the reversals in the age models. But in this case, there was a very nice age model. And the question is why, the question would be to Marcel, if he was here, why the charcoal gives such a good model, and you interpret the dates on leaf walks, interpret it from the point of redeposition, and charcoal was not redeposited. That's my comments, questions to this very interesting, really very interesting presentation. But maybe if Hans will not explain, Hans is here? No, probably Hans also left. Sorry. So it's just to our discussion, and well, and also I would like just not to take more time next time to the talk of Willem Tunen. There was a question why in the Middle Holocene there are peaks of CPDF in charcoal, in radiocarbon dates, which are not supported by the peaks in OSL ages, while in the late glacial and late Holocene, peaks in radiocarbon are supported by OSL ages. From my point, I would suggest explanation. Maybe if your mid-Holocene radiocarbon ages are stability dates, not change dates, but stability dates. So they could have been obtained from peat, for example, or buried soils. Then it means that there was a lack of mineral sedimentation at that time, and so there was not material for OSL dating. Then maybe that may explain this, well, not discrepancy, but the fact that there is no OSL peak there. Thank you.
Yeah, Andrei, if I can respond to that immediately. Yeah, I think you're partly right. Most of the time in this fluvial setting, you either have organic deposition or clastic deposition. They don't go very well together, because if you have a lot of clastic material input, you don't have peat growth in the same valley where the water and the sediment can go. However, what is also an issue in the mid-Holocene level is that you often have to peat. So if you can date the sequences you want to date with radiocarbon, it's much cheaper than the OSL date. So for the exposed late glacial younger dryas terraces, often a lot of the sediment, the classic sediment, is exposed at the surface, so really easy to get and easy to sample. And also for the more recent times, the point bars and the levees. But for that mid-Holocene section, I think the clastic sediments are often quite a bit down, also covered by a clastic cover, which is later by the deforestation and stuff. So last 4,000 years, there's kind of a drape on top of those. So the sands that you want to reach for OSL dating, they are much less easy to reach for that period. So that's an issue as well.
Okay, thanks.
If I'm allowed, I have a question for Anna Gies. I'm not sure if I pronounced that correctly. The talk about New Zealand. Is she still here?
Yes, I see her.
Yeah. Hello.
Yeah.
Sorry.
I thought it was a really interesting talk. Since you are in the Wanganui Basin, did you see any effects of the Taupo eruption? There's a massive volcanic area there, pretty close to the catchment.
No, actually, it's there is some tephographic layer, tephra, is it?
Yeah.
But it doesn't reach the area where we are where we are working. It stops a bit north.
Yeah, but this is what is a VEI7 eruption, and it's pretty close to the catchment. I know it's not in the catchment, but it's pretty close to the catchment. So you might expect that your vegetation was probably scorched or burned or something there, and that may have generated also large volumes of sediment in the upper parts of the catchment. So do you see anything happening about 2,000 years ago? Because we worked in the Wanganui River a bit further northwest, and there we saw a big pulse of sediment coming in at about that Taupo eruption. Even though that river is also not in the
I haven't looked. I could look at the age more closely because that was not the subject of our study, but very interesting indeed. Maybe there could be an effect. I should look into it. I don't have any evidence of it here, but that could be. There was an age that was quite weird, so that might explain. Some age because we do single grain. So if all the grain are well bleached, the age is too, well, not too, but too young. And there was one sample where it was the case. And I thought about a big fire or an event that could have make it change. And it's around 3,000. So I will look into it.
Okay. Yeah. And another question, if I'm allowed. Indeed, in the past, we also looked at deploying OSL dates on the northern island of New Zealand. But it was advised to us not to do it because the quartz grains were too young and they were not good material to capture the OSL signal. So did you have any problem with that? Did you use quartz grains? Or?
No, we did. We use only feldspar. Yeah, for the exact reason you just cite. Some people are looking into quartz sensitivity instead of age to understand other stuff, but no, quartz are too young in New Zealand. So the signal is too dim and especially in single grain, you have 2 grain over 100 that give a signal, while for us it's like 50 grains that give a signal on a disk of 100, so it's a good response. Actually, with 2 discs, you can have a pretty good age. So 2 or 3 discs is the best. Yeah.
Thank you.
Well, if no questions, no comments, maybe we can finish this section and this day. Thank you, Pedro, much for your convening this section, and see you all tomorrow at 9, 10, 11, depending on the time zone where you are. And tomorrow we have a change in our conveners. The first session will be convened by Tobias Lauer, and the second by Alessandro, who is busy tomorrow morning in the university. Well, thank you all, and see you tomorrow. Well, bye.
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 See you tomorrow.
See you.
Thank you. Bye.
Bye-bye.